graph. All right, so in example A, we're going to graph f of x is equal to 1/2 x squared. So we can tell because it's an x squared that it's a quadratic function. And we also know from our transformation section that that 1/2 in front is going to take the basic parabola and it's going to make it widen out a little bit. So in other words, it's not going to be as tall and skinny, it's going to be a little more wide and fat. And so we can basically know the general shape of the graph is going to be a parabola opening up. It's going to be anchored at the origin because we don't have any transformation for the vertex, but we can get more detail by actually plotting kind of 5 classic points. Let's go ahead and do that. We'll do x and y, right? And as I said before, we know the vertex is going to be at 0, 0. That's the default vertex if there's no transformation that's occurring in the function. So it looks like we don't have anything that's shifting the vertex to the left or the right, and we're not going up or down anywhere. So basically 0, 0 will certainly be that value. You can check that by plugging in 0 for x squared, and of course you see it gives you y to be 0 as well, or f of x. Remember, y and f of x, of course, are the same thing. All right, so let's go ahead and put the other points in though. So kind of classically, it's -2, -1, and then 1 and 2, right? Those are the classic points that people use usually to plot. If we use -2, well, you square -2 when it goes in for x, it'll become 4, and then half of 4 is 2. If you put 1 in for x squared and square it, you get +1. 1 times 1/2, of course, is 1/2. And putting +1 gives you the same answer, and putting +2 gives you the same answer as -2. So you'll get 2. Okay, so those are your points, and if you plot 0, 0, the vertex there, on the graph you have that point, then you have -2, 2, so you'd move over 2 up 2, there'd be a point there, and then -1, and then 1/2, so maybe around there, and then do the same on the other side, 1, 1/2, so about there, and then 2, 2, so we end up with a point there. And so basically here's the parabola. And that's it. Of course, you could put some more points if you wanted to draw it, just be a little more careful as you go up and make sure that you're making it wide enough. You could do that. You go out to say 3 or 4 and continue doing the work. However, I think for our purposes, that's good enough. And that's basically what the graph looks like. Let's do the next one as well. For the next one, we do have a transformation for the vertex. So remember, we learned that the vertex has the point h comma k, right? So here's h and here's k. Now, you may not remember where that comes from, so let me just go ahead and give you a little formula here to help you understand that. So basically, the generic form of a quadratic is as follows. We would actually say that it's f of x is equal to a times x minus h squared plus k. All right, so what this is basically doing is giving you the structure of a quadratic equation, and it's doing it in a way that's basically the result of completing the square on the sort of standard ax squared plus bx plus c scenario. So with that new form of the equation, you can tell some things, right? A, for example, will tell you if it's positive or negative, whether the parabola opens up or down, right? Remember, if it's positive, it opens up. If it's negative, it opens down. The h tells you where the x-coordinate of the vertex is, while the k tells you where the y-coordinate of the vertex is. So that's very handy to have. So when we look at our equation down here, you can tell that a is 1, right? Which means that the parabola is going to be kind of standard in width, right? Unlike the one we had in example A. In example A, it was a little wider than normal, but here, because the A is 1, right, the A in front here is just 1, we don't have to worry about it being wider than normal. It's just going to be a standard size parabola. It's also not going to be skinnier than normal either, right? 1 is just the standard shape. And then we have H for the x-coordinate of the vertex, and we have k for the y-coordinate of the vertex. Those are visible from the structure of the equation. So basically, we can plot now very easily. We know this parabola will open up. We know that it'll be located at a vertex of, so let's write that out first. The vertex is going to be equal to h comma k. And in this case, that means the vertex is, now here's the thing to remember though, the h inside the parentheses, you don't take the sign, you take the opposite sign. So if it's -2, we're going to call it +2 here, +2. And then for the k, we're going to actually take the sign, which is -3. That's why in the formula you see that there's a negative in front of the h. They're trying to tell you that take the opposite sign of what you see, whereas there's a positive sign for the k, and they're trying to tell you, therefore, just take the sign that k has. So that's a little bit of a thing to remember, right? Just remember inside the parentheses, it's sort of opposite world, right? If it's -2 in there, it's +2 outside for the vertex. So either way, the vertex for this is going to be 1, 2 over to the right and down 3, 1, 2, 3. So that's your vertex right there. And then once you have the vertex plotted on your grid, you're going to then just basically plot some points if you want to, just for good measure. You can do that by creating an X and Y grid here like this, and then picking kind of points that are nearby. You don't have to do the standard points of, say, -2, -1, etc. You can skip those, and you can actually look at the parabola here and recognize that it has sort of an axis of symmetry, right? So before we had the y-axis over here in this graph in A, we had the y-axis here being the axis of symmetry. In other words, you could fold the parabola in half over that y-axis, and they would lay on top, the two sides would lay on top of each other. There were mirror images around that axis. Well, here in example B, we have something similar, but it's been shifted over 2 places to the right because of that change in the x-coordinate of the vertex. And what that means is that we might want to plot things around that. So, in other words, the point that's right next to that on the x-axis would be, say, this point here, right? So on the x-axis, we might choose 1, for example, right? And we might choose 0. That's 2 steps away to the left. And if we went the other direction, going from here and here, right? Those would give you now, those places on the x-axis would correspond to x equals 3 and x equals 4. So we can use, for example, 3 and 4. So we're basically coming up with points that are on either side of this axis of symmetry, right? All right, so let's see what happens when you plug 1 into the function. Well, you would have 1 minus 2 squared minus 3, right? Well, 1 minus 2 is going to give you -1, and that'll be squared, and then minus 3. Well, when you square -1, you get 1, so 1 minus 3 gives you -2. So you get -2. Now remember, 1 was right here on the x-axis, right? It was just to the left of that axis of symmetry. So the point just to the right of it, in other words, 3, is going to have the same exact answer. So we can just put -2 here and say, hey, that's going to be the same solution. You can check that, but you don't have to. You can trust me that that will work. Of course, go ahead and check it for yourself so you know that 3 does indeed produce the same result. All right, let's put 0 in now. All right, if I put 0, I'll have 0 minus 2 squared minus 3. That'll give you -2 squared minus 3. That'll give you 4 minus 3, which is the same as just 1, of course. So we'll get 1 here. And again, the 4 will give us the same answer because 0 is 2 steps to the left of that axis of symmetry. 4 is 2 steps to the right. Remember, because it's symmetric around that line, we're basically going to have the same answer for any point that's equal distance from that line. All right, so x is 1 minus 2 for the first point. So we're going to do 1 and down 2. That's here. Then we have 0, 1, so at 0 on x we go up 1 to y, so that would be there. And then we have 3, -2, so 1, 2, 3, and then down 2, right? And then we have lastly 4, 1. So out 1, 2, 3, 4, and then up 1 on the x-axis. And there we have it, right? So we have our drawing, and that's good enough. All right, if you wanted to get some special points maybe that I didn't include in this graph, you could look for the intercepts, for example, and you might be interested in the x-intercepts. We have the y-intercept. You can see where it crosses the y-axis, so that's good, but we don't have x-intercepts labeled here. You can see that it crosses the x-axis in the drawing, so it might be worth figuring out where those points are located. Those points are also referred to as the zeros or the roots, but for now we'll skip that. We'll look at that in another video, but for the moment, if you want to try that on your own, you can just basically set f of x equal to 0, so set y equal to 0, and then solve the quadratic equation that results, and the two answers there would be your x-intercepts.